What do you think of that? How convinced are you?
Pretty convinced.
Pretty convinced? You're like, well, it looks okay. Lines up with what my tutor already told me and what the textbook says, so should be okay, right? Should not be okay. You should not be satisfied with that. I totally did hocus pocus on you, okay? Because even if I got to some legit results, do you know did you pay attention to how many times I fudged around during my explanation, right? I was like, well, it kind of looks like this, and it sort of might go through there, right? I was making up a lot of stuff, okay? They talk about mathematical proofs being rigorous, right? Which is like, it's watertight, there's nothing wrong with it, you can't poke any holes in it, okay? That was, yeah, what's the opposite of watertight? That has holes everywhere, okay? So we need to do a little better than this, right? This is nice, you can see the principles, but we need to be a little more rigorous, okay? So, hold on, step back. How do we usually get derivatives? When you're starting off and you're trying to meet a function for the first time, what's the first thing you do? The first thing you do is first principles, okay? So let's give this a go. I'm going to get rid of this graph. How many of you even remember how first principles works? I'll give you a clue. It starts with F dash. That's the easy part. Okay, alright, help me out. Together we can do this, right? What's the next thing? I haven't heard the right thing yet. Before the F, there's a limit. Yes. Why? Why is there a limit? Why is there a limit? Because what I'm about to put down here is a fraction. What fraction is it? It's rise over run, isn't it? Rise over run. But rise over run works when you've got this point and that point, and you're working out a gradient between them. But the whole point of calculus is to not have 2 points. It's just to have it at 1 point. Hence, limit. Okay? Alright, so what is the thing we're calculating? F, x plus h, minus f of x, all over h. Okay, and remember, this is just rise over run. It's just so it happens that the 2 points you're thinking about, right, have a distance of h between them, right? And when you looked at these two y values, you've got f of x and h over here, and f of x down here. So if you want to work out that distance there, there's your numerator. Okay, so it's just rise over run. It's y2 minus y1 on x2 minus x1. That's all it is, just with fancy weird notation on it. Okay? So we're trying to work out sine, aren't we? And we're trying to show it in a kind of more rigorous way. So, help me out. What's going to appear over here? Everywhere I saw f's, I'll just put sines, right? Sine x, all over h. Are you content with that? Does that look okay? Cool. What can we do with this? What kind of options do we have? All I can do is expand, really. By the way, why would I do that? What is my goal in this situation? I need to somehow get rid of this h, or put it into such a form such that I actually can substitute h in, which I can't do right now, but I want to work toward that. Okay, so I'm not just doing mindless algebra, I have a goal in mind. Okay? Maybe you do feel like you're doing mindless algebra, that's okay, we can just try and file it in the back of your mind there. What's the expansion? Sine x cos h plus what? Cos x sine h, and then you've just got that sine trailing off on the end. All over h. Okay, now stop and look at it for a second. What could you do with it? Because we've just done the expansion. Wow, I really write wonky, don't I? What could I do with this? What kind of options do I have? Remember, my goal is to get rid of the h or put it in some form where I can just evaluate it. I can certainly do some factorizing here, right? The question is, what can I factorize? Well, I've got these two terms here that both have sine. So that's a start. Let's work with that. Okay? So I've got limit, as h approaches 0, of, okay, I'll put my sine terms at the front. Right? What will I have? I'll have cos h for that one. For this one, I'll have minus 1. Okay? Now that's all over h. Now you're like, hold on, the fraction's not finished yet. I know it's not finished yet, but see this guy, he will never work together with this guy, okay? Because you can't factorize him well. You could try and do this thing here, okay? But I will save you some time and tell you that you will not get very far, okay? You might as well just leave it as a cos x, okay? But I'm going to do this. I'm going to separate out the limit, okay? The limit of a sum is the sum of the limits, okay? Because this is calculus we're talking about, right? So therefore, I can stick this guy over here. Okay? Now, we factorize that sign out, and we've got a cos here, right? These are both in x. Now tell me, what happens to sine x, as h approaches 0? What happens to sine x? Answer, nothing happens to sine x, because it has no h's in it. So h is doing its thing, approaching 0, and sine x is like, yeah, just whatever, man, you just carry on, okay? So seeing as it's independent of h, right, I can actually bring it out the front. We're not used to doing that, because we're like, it's got a variable, you can't just muck around with it. It's like, well, it has a variable, but it's not the one that I'm worried about, okay? So it's independent, so I'm going to bring it out the front, okay? So I've got a sine x out here, and then I have my limit as h approaches 0 of this guy. Okay, now I have the same thing happening here. It's the limit as h approaches 0 of, sorry, no, I meant to write cos first, sorry. And take the cos out, then write the limit, and then I get this. Wait, how did I get, that's a really messy page. Let's try. Alright, now, have a look at this with me. What kinds of conclusions can we draw about this? Let's have a look at this guy first. Let's have a look at this. You got cos h minus 1 over h. Cos h minus 1. Now, what's happening to cos? What's happening to cos as h approaches 0? Well, you know what cos looks like. It looks like this guy. Get rid of that. Okay, there's cos. Okay, now we're used to graphing this in terms of x, but I've got h's, so there's h. Okay, and this vertical graph is cos h. So as I'm approaching h approaches 0, right, from both sides, I'm going in here, and this is what I'm getting towards. What's happening? I'm approaching 1, aren't I? In fact, I don't just approach it, I do get there. Okay, so up on top here, I have 1 minus 1, which is just 0, right? What does that mean? I've got 0 there, but what do I have on the denominator? I also have 0. But here's the important thing, okay? I'm approaching 0 on the top, and I'm approaching 0 on the bottom, okay? But they're approaching 0 in different ways. They're approaching 0 in different ways. Just like if I showed you this, I said, let's graph this rational function. It looks like this. Okay, I'm going to make that a +1. Okay, and I said graph it, and I could tell you instantly it has an oblique asymptote. Why? Because the power of the top is bigger than the power of the bottom, but so what? I'm thinking about oblique asymptotes and horizontal asymptotes. They're about limits as x approaches infinity, right? Right? And I would say, well, what happens to this? It approaches infinity. But so does this. They both approach infinity, don't they? So shouldn't it be like infinity and infinity? Shouldn't it approach 1? That sounds like a horizontal asymptote to me. How can you argue that it's an oblique asymptote? Aha, okay. So they're both going toward the same place, but one goes faster, right? One goes faster, okay? So now my question to you is, cos h minus 1 and h, they're both going towards 0, but which one is going faster? Or are they going at the same rate? Because those are your two alternatives. Either this guy's faster, or this guy's faster, or they're equivalent, okay? And that will tell you what kind of thing you have. Okay? Now here's the thing, you can go ahead and draw it, right? Excuse me. And you will find this actually tends towards 0. Okay, it tends towards 0. What does that indicate to you? Which do you think is going faster? Or rather, which do you think is going towards 0 faster? The bottom. Because if they're both going towards 0, right, but this guy's going faster, right, then this guy will keep on being an actual number, okay? I want this to be, wait, hold on a second, h? So I say it the other way around, cos h minus 1 minus cos h. I'm going to be confused. Doesn't matter. I know what the answer is, okay? You can actually, you know what you can do if you're not satisfied with that? So you remember what a limit is, right? It's just thinking about how something behaves as you put in successive values, they get closer and closer and closer, okay? Now you actually, because you have calculators, you don't have to guess what happens to this. Okay, you can actually put values in, you can see how it behaves. It'll be sine, I should say it's sine x times 0. Okay, which, right. Now then I ask, well, what happens to this guy? You have a similar kind of scenario, don't you? Don't you? Sine h is going towards 0. H is also going towards 0, right? But which one is going faster, or are they going at the same rate? Now, have a look at sine. Now, if you go ahead and you actually draw this properly to scale in radians, and you put y equals x on there, you'll get that. Okay? And if you zoom in here, you're just going to get, go this way. These are really, there we go. They just get closer and closer and closer together, right? And they never actually diverge. They never go apart. They're always going toward at the same rate. So therefore, this guy is actually approaching not 0, but 1. They're going to the same place at the same rate, right? Just like, say, if I did this, and I said, well, as x approaches infinity, they're both going to infinity, but they're going there at the same pace. So that's why you get a horizontal asymptote for that guy. Okay. So here, I'm going to get this. Okay? Because this limit is approaching 1. So this disappears and you end up with this. Okay. How convinced are you? Well, I'd like to say it's a little better than what we did the first time. I think it's an improvement, okay? Because before I was just like fluffing around, but my drawing was actually pretty bad. Like it was not symmetrical, and I was just hoping that it would look okay, right? Here at least you've got some algebra to back you up. But where was the problem? If there was a problem. It's all about these limits, isn't it? These limits are the real issue, okay? In order to get from here to here, and here to here, I actually resorted to the same thing I did in the first place. Which I said, hey, look at it, and that was the length and breadth of my argument. So can we do something a little better than this? It's called the squeeze law. You're like, really? It's really called the squeeze law? Yeah, really. Go and wiki the squeeze law. That's what it's really called. You will see why it's called the squeeze law in a second. It's a brilliant name. That's exactly what you should picture. Okay, now, just one quick thing. See this graph of sine against x, okay? I want to put one more thing onto it, keeping in mind, whoops, that's not what I want. I want here. That at x equals pi on 2, right? If I graph tan x on there, what's tan x doing as it approaches x equals pi on 2? It's just rising off to infinity, okay? So it's doing this. Okay, and just have a look at that for a second. Okay, I've got tan, I've got x, and I've got sine. Okay, tan, you just told me, is rising, and it's rising faster and faster and faster and faster and faster, all the way up into the asymptote. In fact, it never even gets the asymptote. Okay? Then you've got x. How would you describe its growth? Constant. It's constant. I mean, we could say it's linear, but that's sort of by definition it's linear. It's constant. It's just sort of chugging along at its own little rate. It's not getting any faster. It's not getting any slower. What about sine? It's increasing. We said that at the beginning, but it slows down. Eventually, it runs out of steam. It's like, I'm so tired. I'm going to roll down this stupid hill at Fagan Park or whatever it is, okay? It's increasing, but at a decreasing rate. So therefore, in that domain, for 0 to pi on 2, I'd like to suggest this inequality. Sine, poor guy, he just runs out of steam. He's the lowest guy on this rung of the ladder, okay? X is bigger than him, and is always bigger than him in this domain, right? Because as soon as they're out of the game, maybe you can relate to this. There's your, like, you know, slow and steady wins the race. Guy is training for the city to surf. He's just chugging along. He knows the pace himself, right? Poor sine X. The second he starts running, he's like, I'm already slowing down. Okay? So sine X, slower beneath X all the time. And then there's that one guy who's like, I hate that guy. He's year 12 and he's still fit. What's wrong with him? I don't care if he's a sports captain. Whatever, you know. He's running, and he's just running faster and faster and faster, right? He's like, I'm just getting warmed up, guys, you know? So there you go. There's, I don't know, that's like Mr. Knox or something. He's quite quick. You better watch out for him, okay? So I'm going to say for this domain, this is always true. Are you okay with that? This is reasonable. I think you can zoom it, you can graph it to scale, plot points, prove it to yourself. I think it's true. Okay? Now I'm going to do something a bit weird with this. I'm trying to think about this. Remember this guy? This was our issue before. This guy is hidden in here. It's just not that obvious. Okay? I can put him in if I divide everything by sine. Watch. If I divide everything by sine, 1, 2, 3. I know you're not used to dealing with 3 inequalities, but they follow exactly the same rule as if you had 2. Okay? I'll divide this through, I'll get 1 there, because I divide by sine. In the middle, I'll get x on sine x. Okay? You're like, no, wait, you wanted sine x over x. As you'll see in a minute, it doesn't matter. What will I have on the right-hand side? I'll have 1 on cos. Okay? Now, I'm interested in what happens to all of these things as I get closer to 0. Remember that? That was my fudge, right? So I want to fix my fudge, okay? So I'm going to take that didn't come out the way I meant it to. I'm going to take the limit as x approaches 0. You okay with that? 1, 2, 3. This should all be true. The limit as x approaches 0 of this should be less than the limit as x approaches 0 of this should be less than the limit as x approaches 0 of this. Okay? You content with that? I've just gone across the board, applied limits. So tell me, O astute year 12s, what happens to 1 as x approaches 0? Answer, nothing. He's just standing there and like, you just keep amusing yourself. I'm just going to stay what I am, okay? I'll leave this guy for a second. Less than. What happens to 1 over cos? Now, I actually know what happens to cos as x approaches 0. You told me before it approaches 1. So therefore, the whole thing approaches 1 over 1, which is 1. And then, of course, we have this guy left in the middle. Now, this is you, the awkward, uncomfortable third wheeler on that date, okay? You're like, why did I agree to this? This guy is greater than 1, but he's less than 1 as well. He's being, do I have to say it? Okay. So what's going on? The squeeze law says if you have some variable and you can show that it's always between, it's less than some value and greater than some value at the same time, guess what? You can say that it's not between the values. The only thing it could be is that value. Okay? You're being squashed between them. Eventually, at some awkward point, you become that value. Okay? Remember, I'm thinking about a limit, by the way. Okay? I'm thinking about a limit. So a better way to think about this is to try and peer into what's happening here. Right? Tan x and sine x, you guys getting faster, and you guys getting slower. Now let's reverse the time. Let's go back towards 0. What was happening at that point? Everyone was running at the same pace. Namely that. Okay. Now here's the reason why, by the way. 1, what's the reciprocal of 1? 1. So if I take the reciprocal of the right-hand side, I should be able to take the reciprocal of the left-hand side also. So a corollary of this is this. This is also true. It is just as true as the previous statement. Okay. Now, just as a side note, it's not the primary thing I was interested in, but I can play exactly the same game here that I played with sine. I can play it with tan as well, can't I? What would happen if I divided everything through by tan? What would I get? What would I get on the left? Divide sine by tan. Divide by sine by tan, which is the same as multiplying by cos, which is cos, right? You divide the middle by tan, you'll just get that. And then you divide the right-hand side, and you get 1. You take your limits. Now, let's skip this line here, okay? What's the limit as x approaches 0 of cos? It's 1. What's the limit of 1? It's 1. So you can squeeze this as well, which means you can squeeze this as well. They all approach 1 as you go closer and closer to naught. Okay? These are actually some semi-important results. So now, I've got this. I have this in the bag, and this guy actually follows from that. Okay? How happy are you with that? Does it feel a little more watertight? It should. It is better. I've handled these. But you should still feel uncomfortable because I'm still pulling the wool over your eyes. Did anyone pay attention enough to notice when I did it? When did I do it? You should always be really suspicious when I say, let's just have a look at this. And you should be suspicious when I say, are you happy with that? Right? Because, yeah, that's always me trying to be a little shifty and saying there's something going on here. I'm just going to ask you to accept it but not tell you why. Okay? So therefore, what I really want to go after is this. This is the final piece of the puzzle. Okay? It really. There are no more, what do you think of this? Let's consider. Okay? If I can get that without a shadow of a doubt, then I can get to here, which can get me to here, which can get me to here, which we can, you get the idea. Alright? So, are you ready? What did this topic start with again? We started trig, and what did we start looking at? Oh, we were doing trig? I forgot, sorry. We started by looking at radians, right? And immediately we used radians to measure what kind of shape? Circles, because they come from circles, okay? Draw me a circle. Draw your circle. Here's a circle. I've got a center. I also have a tangent here, which means that what kind of angle do I have between the radius and the tangent? 90 degrees. Great. Let's finish this quickly. Okay. I promise this will be good. Now, have a look. I want to compare 3 shapes here. 3 shapes. And this time, there's no more, oh, what do you think? It's just beyond a shadow of a doubt. Okay. The 3 shapes I've got are this triangle in here. Let's call it radius R. Okay. This sector and that big triangle I drawn. Okay. Now let's just call this theta. Tell me, what's the area of the triangle? Half what? Actually, sorry, I should call this x. Half what? It's just the triangle, Half r squared sine. Now, do you agree that triangle must be, without a shadow of a doubt, smaller than the sector that it's sitting inside? Must be. Because the sector is always going to add that little segment. No matter how close they get. Okay. So this is always going to be less than the sector. What's the area of the sector? Don't forget the angle is x. It's r squared. It's just the sector. It's just x. You're used to saying theta. Right? Okay, now do you agree that that sector we just talked about must be smaller than, without a shadow of a doubt, this triangle that goes outside the circle? There's no way it can be bigger than that triangle. Okay. So what's the area of this triangle? Well, I just need a half base times height. I know what the height is. What's the length of this side? Now, I've got an angle and a side. This is the adjacent side, and this is the opposite, right? So this length should be, if I am calculating this, r tan x. Is that okay? Because tan x would be opposite on adjacent. Okay? So the area of that big, huge triangle is half r squared tan x. Okay, ready? Ready? 1, 2, 3. Happy? You gotta say used to me. It's like, no guys, I'm not the boy who cried wolf. There really is, it really is true. Okay.